Good afternoon, everyone. Welcome to our 11th lecture for the Postgraduate Dynamics course MSD 780. Today we are going to start with our first of two guest lectures, and our focus is going to be a bit on a commercial simulation software packages regarding multibody dynamics. So up to now, we've had a look at the underlying mathematical principles and some of the more scripted versions of solving complex multibody systems, when in fact we have some commercial software packages available that can definitely ease the manner in which we utilize the packages and the dynamics to make it much more user-friendly to us. And one of those packages is MSC Adams. Now, I wouldn't really call myself a specialist in the field of Adams, so instead I reverted to our guest today, Mr. Gael Mutombo, who's going to give us the two guest lectures with regards to the use of Adams and how we can solve complex multibody systems using it. So Gael is from SIMTEQ Engineering, which is an engineering consultancy specializing in the use of commercialized simulation software packages and their use in the mechanical engineering environment to solve various types of problems. And they also provide some training and development courses. So I would highly encourage you after the session to go and have a look at SIMTEQ Engineering and see what they have to offer. I'm sure you'll definitely find something to your liking over there, considering your specialist field in dynamics at this stage. But without further ado, I'm going to hand over the stage then to Gael. And yeah, Gael, we're very interested in learning more about Adams, so the floor is yours.
Okay, good evening, everyone. Before I start, I'd like to check, could you hear me properly?
Yes, sound is good on my side, Gael.
Okay, thank you. So, okay, my name, as they all said, my name is Gael Mutombo. I'm a mechanical engineer at SIMTEQ Engineering. We are actually a consultancy company. We work with most of the mechanical manufacturer in sub-Saharan Africa and also in UAE. But we are more focused in South Africa, since most of manufacturers, those who go from R&D to manufacturing, are located in South Africa. To start the lecture, I will just share my screen so that I'll be able to present it. Okay, just a minute. It should be fine now. I cannot see that on my side. Okay, so now it's working. Okay, as I said, I'm a mechanical engineer from SIMTEQ Engineering. I'm also I was graduated last. I got my honors degree in tax, and I'm actually also a master's student at tax. The lecture of today will be split as follows. I will give a brief introduction of what is SIMTEQ Engineering, what we are doing, and which type of solution we are representing in South Africa, in sub-Saharan Africa. I mean, and then I will go to present a challenge. This is actually not really something we get a mark for. It's an idea to make you understand more how we use multibody dynamic simulation in the industry. So I will briefly present the challenge. I will, at the end of the lecture, send to Devolt. The file necessary to run the challenge will be for you to have a look at it and play around if you are interested. And during the second lecture, I will give you more insight on how to solve the problem. Then I will talk about Adams, a brief history of how it's used and how it has been created. Then we talk about why we use multi-dynamic model in the industry. After that, we go for virtual prototyping. That is a concept really important to understand the field of simulation, not just for multibody dynamic, but also all different fields of simulation you can find in industry. Then we go to I will give a little presentation on Adam interface and the different wizard you can use to get some results out of the simulation. And then I will go on rapid prototyping. Rapid prototyping is a concept used in industry to go from a square to a bolt and nut type of design. So there is two different, let's say, two different ideology in South Africa. There is those who prefer to hard design everything, create physically and do many iteration. And there is also people who want just to do everything virtually. When they are ready, they can now build everything physically. I just have to check if everyone can see my screen. Are you able to see my presentation? I don't want to speak in there just like that.
Yes, Gal, we can see it. Thanks.
Okay. Okay, so SIMTEQ Engineering started in South Africa as with the name of SIMTEQ MSC Africa in 1995. Then we moved from that name to STEC, and then we finally got the name of SIMTEQ Engineering in 2019. So mostly we supply the products of Hexagon AB, that it was known as MSC software. It's actually the most popular name because it was the first one. But this is more on the mechanical engineering field. And then we provide also software for injection molding and a bit of civil engineering. So Moldex 3D is for injection molding, and the rest is for civil engineering. So we are specialized in CAE simulation. Technically, we tend to master all type of CAE simulation we can have we can find in mechanical engineering industry. That this doesn't mean that each of us in the team master all of that. No, we are complementary. So I have some knowledge, and my colleague also has the other knowledge. So what we do is we supply the technology, we do training, we do support for companies, and we also we also transfer the knowledge. And when you talk about transferring the knowledge, we are talking about more what is happening in academia. For instance, what I'm doing right now. For everything about supporting and training, this is more in relation with people who want to learn, the technology, or people who just cannot do it because they don't got the background, or they don't have the workforce needed for them to get the technology. So we are more focused on optimizing engineering and money. This is really important, especially in South African market, because we all run, or most of us run, with limited funds. The good thing is South Africa is the biggest market in Africa. That is a good thing, but in the world, at the world scale, we don't have the same fund as a company in US. So it's really important for any engineer to come in the market with the idea of how to develop a product while spending less money. Also, we want to gain insight into engineering problem to develop better solutions. This is really is really related to what it's really related to the challenge that I will give you, where you have a product, and it's not that the product is wrong, but it's more that we need a new solution, or a better solution, to either save the cost or save the material, but also bring everything to the cost. And this is the team of SIMTEQ Engineering. We are actually six engineers with different knowledge and different level of experience. As I said, we cover the all sub-Saharan Africa. Sorry, let me put the laser so I can point it. So we cover the whole sub-Saharan Africa and also the UAE. And the funny thing with the UAE is just because South African engineer was hired there, and they requested us to support them. Is how we move there. As I said, this is exactly the mission as I mentioned. Just to give a little bit of history, the simulation, actually MSC software was the first simulation simulation technology to be created. It was created for the space program of US, where MSC software was appointed as the company to create a solver that can calculate all the trajectory of the rocket in the space. Not the trajectory. Sorry, I meant the stress calculation on the rocket during its trip in the space. So I'm not going too far to how we move from there to then develop all the simulation. But at the beginning, it was just a solver, and then progress was made to add a user interface, to add other type of simulation, because at the beginning it was just load that was evaluated. Then we had sound and CFD. And this is what MSC software is about. It's actually everything in the market that have a sort of physics that the theory is known and well mastered are likely to have a simulation technology that go with that. And the reason is simple. As you have seen in MSD, when you deal with the script, it can be some action can be repetitive and sometimes time consuming, and in the business or in industry, the time is always related to the money. And as I said earlier, the funds is limited. So there is all of those technologies that have been created in almost every sector. We have the medical one, electric one, the railway, automotive, aerospace. I can say some company, for instance, in aerospace, we have Incoma in South Africa, or Paramount, that they are also in defense. We also have heavy equipment like SIMTEQ or RAM equipment. And then we have food industry. As I say, railway, we have Transnet for the railway, and electronic and energy. No, we have energy and gas. We have ESCOM or OPEC, for instance. So, as I said, the presentation will be split into. We have on the day one, I will give the basic of multibody dynamic using Adams, and then on the second day I will go a bit further by giving more, I can say more interesting but more advanced theory or concept that are typically used to enhance a design. So today we will focus on creating a design, everything that you need if you want to create a design. How do you test it? Which type of data do you get from that? Then on the second day, we're gonna learn how to use those data to create more advanced design, or how to create complex simulation. The reason for that is when you deal with simple simulation, you are not really recreating what is happening outside, and you will see that sometimes you just have a constant torque, for instance, applied on the system, on a shaft, for instance. You can also have a constant speed. That is not always the case in reality. Where the purpose of doing a simulation, especially in industry, is to get a simulation as much as possible close to the reality, so that we can evaluate how the system will behave in the future. So This is the challenge I just mentioned. So what is happening here? I can I have to remove this. Okay. Okay. So what is happening? What is happening? We have a toy. This is actually a gun toy, but with an issue. As you see, the bullet is when you trigger it, the bullet is not going far, and the reason for that is the there is four different spring damper. No, is more spring in the system, and the question is how which spring do we have to choose, or which combination do we have to choose if we want to get a certain result. For instance, with this simulation, we don't even get the 30 centimeters out of the gun. But like the question would be, if we want the bullet to reach 5 meters, what will be the combination of spring that we have to put inside the system so that we will reach that target? And knowing this is a toy for kids, that means we cannot exceed a certain amount of force applied on the trigger. There is actually a standard value for kids that is supposed to represent the amount of force that can be applied by the kid's finger. So knowing all of that, how do we design a an accurate model? As you see, this is a final product, something that has been manufactured already, but now you sit with a problem where you don't have it, or you don't have the final results. I agree that someone can find a way to do it manually, but this is not the point. The point is, if you have 1,100 model like this, you cannot do it by hand. It will just take too much time. At this level of production, at this level of problem, you need to use some kind of technology that will help you to quickly get to the answer, or to have an insight of what will be the answer to the initial question. So Adams, it's not just a good name. It means automatic dynamic analysis of mechanical system. It's used to solve actually multibody dynamic, as I mentioned, mechanical system simulation, and motion simulation. It's used equation of motion that are generated by the model. And when I say generated by the model, it comes from the all the parts inside of the model. That means the geometry that is used, all the joints, all the different joints, but also the force applied in it. So and it's actually a non-linear solver, because it can solve, as is written here, a large angle, large displacement, and non-linear forces. And it has been created. It has been created in 1974 at the University of Michigan. So at the beginning, it was not a commercial product. It has been bought by MSC Software afterwards, but it was initially a university project. So to the question, why build a multi-body dynamic model, is firstly to identify what we have in the model. And what I mean by that is, firstly, to know how the model will move. This is just to see how it will move, how it will interact, which part will be in contact of another one, because there is always a difference between the design that is made for the production than the initial concept. Because the design, when a design is made, actually a CAD file is made, it takes into account some details like welding, like tolerances, but these are not taken into account when you are in the R&D phase, and when we want to first see how the system will move. For a simple system, it's easy to imagine how the system will move. But when we have 100 parts moving and some are hidden behind some other parts, it's just too complicated from your eye to identify this one will move that way and will be locked or touched or will pass to a certain configuration. So this is the first use of Adams. Is just to take the simulation to analyze how this will move. It's valid for Adams, but it is multibody dynamic general thing. When we use a multibody dynamic theory in industry, is firstly to see what will happen or how the system will behave. Then we have to predict what will be the loads created, generated, or applied on the system. And the reason why is because it's difficult to find a company that can manufacture everything from A to Z. And most of the time we have to rely on other companies. That means we have to buy out parts and put it inside. This is the first aspect. The second aspect is when we want to run a FEA analysis on a part, the main question is always where the parts come from. Sorry, where the loads come from, because without that you don't have any insight or any proper insight on how the system will behave, which stress or fracture will be created inside of the system. So the second thing is to explore, the third thing, sorry, is to explore new things inside of the design. And this is mostly when you want to improve a model that already exists, or when you are in the R&D phase, where there is 100 idea and you don't know what to use. And this is something really, really important, because as soon as you will start working in industry, you will realize that there is no good idea. There is only idea that has been tested, that passed or failed. But again, if you are in a room, let's say you are working for a big company, not a big company, a middle-sized company. You have a team of 100 engineers working on a car, and everyone got a different idea. The only way to find which one will pass is to test it. Or if you have someone who have experience and I can tell you this will work or not, but again, this will be a guess based on experience. And if it's a team of young engineers that we can find in many industry, you will need a kind of way to be sure that your idea is a good one before even thinking manufacturing a simple version of your product. That's why you can use a multibody dynamic software to now explore your idea with confidence, because as soon as you start doing the simulation, you have no limit. I mean, you can do crazy things. Since you are not breaking anything, you can do many iterations a day. It will be fine. The limit is always the time to implement it and the time you have available during the day. And then we go to the optimization. The optimization is when you have the results. How do you get an insight from the result, and how do you improve the result? For instance, a simple example is you will see that on the second day, if you have an arm, you cannot decide which one is the best one, but you have an objective function. How do you get there? Obviously, this for most of you guys, this is not concept that's new concept. It's something that we are dealing as mechanical engineer, but it's always good to remind that it's always important, and especially in industry, who tend to go always for first principle to get straight to the answer. So the process of doing the simulation inside of the person of using the simulation follow this path. It's build, test, review, improve, and it's always like that until you get to the bolt and nut level. That means if, let's say, for instance, you want to build a car, you need to start somewhere, and uh, and and the easiest way to start building a car is to do what kids does. You just have a box, you put wheel on it, you have all the initial requirement. For instance, the weight of the car from the beginning, it's known. uh, the range of the car, it's known. The type of wheel, or an idea of type of wheel that you need, it's known. So all of that, and also the soil on which the car will run, it's known. So this is the basic thing that we have when you start the design, and then you just start with a box with four wheels. You get from there, you do your first simulation, and let's say you find the torque on the wheel. It won't be accurate because the design itself is not accurate. You are using only the mass and basic knowledge, but at least now you can remove a lot of type of, let's say, suspension, uh, or a lot of type of engine that can be used for the for this particular car. So the purpose is to narrow everything until you get to a precise design. So as I said, is you build the car, you build the design, you test it, you review it, you improve it, and you start again. So now let's talk about Adams. When you start and you open Adams, you will see this interface that is actually just asking you to create a new model or to open a new model. So if you are at the stage where you can open a new model, you already have some experience or some exposure to the model. But if you have never opened it, when you will click on new model, they will actually ask you to choose a a directory. A working directory is simply where everything will be saved. Then you choose the direction of the gravity, the type of unit you will use in your model, and you simply give a name to the model. Then when you open the software, we have those different parts. This is actually the user interface, where we have the menu on the top with edit view setting and all. This is basic to almost every software. We have the ribbon. You have the ribbon here that is really important because it's how you reset the model. We have bodies to set everything, all the parts, all the different geometry that you use in the model. If you want to apply some particular feature, if you want to change it, if you want to add a marker or a point in the model, and also if you want to work with a flexible bodies. So the principle here is, as you see the first video, I can quickly come if it's not too far, just to show it. Okay. This model actually use a flexible body. Okay, right. Well, at least you have seen that. So this actual model use a flexible body coupled to a rigid body. So the point is, we can use dynamic load and extract it from Adams to apply it on the FEA model, or we can do it while running the model. Adams is not that powerful in terms of running flexible body. It does give some input or some insights of how what is the stress, the displacement inside of it. But at the end of the day, it's always better to use a proper FEM model if you want to work with flexible body. You can actually extract the dynamic load from Adams, but at the end of the day, it will be always better to use a flexible body. Then we have the result here and the tree view, when we can find everything like bodies, connection, motion, forces applied. We have The globe here is the direction of the global coordinate system, and then we have the working grid here. When we are done running this, when we are done setting our system for the first time, we can now um, run it. And the good thing here is it's very simple to run. As I said, the first purpose when they created this software is to make engineer able to see how the system will work. That's why it's simple to run. You can do it in like 1 minute and you are done with your system. And when you want to see to simulate it, you have two things where we two important features. It's the end time, that means the length of the simulation, and also the step size. You can either select the number of steps or the length of the step. In that case, it's just a number of steps. Then we have, sorry, we have the animation. One of the mistake is because we see those buttons on the top, most of people tend to run many times the system. When you have a simple mechanism, yes, it can run really fast. Actually, even at a certain stage, even if the mechanism is complex somehow, it can also be fast, but it's more dependent of which type of connection or which type of constraint you put inside of the system, that the largest of the system. And so I will always advise to just do the animation. If you run it once, do the animation. And I'm telling you, when you're gonna work on a full vehicle and which take hours to run, you are not going to press on run again. And then we have here the plots, but the plot button that can allow us to see, to have an insight of different data that have been set before, actually the data that have been measured. And when you get it, when you press on the plot button, we open the post processing part of the software, on which we can do two things. We can either animate it again, or apply the just plot the curve. And at a certain point, when we have particular case and you want to see at which point of the animation we have a spike in the curve, for instance, we usually split the grid so that we can have the animation at the same time as we have the curve. So, and then you have a cursor that runs through the curve at the same time that the animation is running. So on this side, you can decide if you want animation or the plot. We have the tree view on that side. The property editor is on what you can see here is the animation mode. So we have the property editor here, and then we have the ability to run or to modify different parameters of the animation. Also, we have the viewport. We have the viewport, not actually a working grid. And the toolbar. The toolbar here is really important because it allows you to have different insight of the software. Either you want to just see something, or you want to analyze something, or retrieve a specific part of the analysis you will really need the main toolbar. And again, this when you go on the plotting view, and on this particular curve, it's just overlapping two different curves. For most of the time, you just to see the difference between them. And again, you have the property editor on the side here, and this is all the results that have been measured during the simulation. So it can appear on two types. You can either select it. That means there is results that are measured anyway, but there is some other that are not measured, and you have to pick them. You have to set them so that you have the result that you want. And also there is different way of getting a result. And I will get to there a bit later on. So to just illustrate what I explained, I will give you a simple example of a pendulum and which type of result that we can have. The thing that you do realize is at this stage we don't properly represent a system, and the reason it's simple is we use rigid body. The truth is, in the reality, there is no rigid body. That means when we are using a multibody dynamic, we are getting insight. Right? We are getting insight on something, but a full simulation actually required, or what you call a co-simulation, where you can mix a powerful FEA model coupled with a nonlinear FEA, coupled with a CFT, coupled with a multibody dynamic. This is life, but it also really expensive. It's not always practical, but at least you have the insight. Yes, you have the insight inside that. Then we use ideal joints. This bring a particular challenge, the fact that there is no ideal joint in the real life. So we always have to bear in mind that at the end of the day, um, a simulation is as good as the engineer that use it. That means that you have results, uh, you will have more results than what you get from a script. For instance, when you hard code something, not more results. The good expression is you're gonna get that result easily, at least easier than when you use a script, but you still have to analyze it, and it's just surprise. It it's difficult to realize that, but there is a lot of people who still think that the simulation is accurate no matter what. Mostly there are people who just started using that in industry or didn't go to background during the undergrad for many reasons. But you need to keep it in mind that the simulation is as good as you. If you put the wrong parameter, you're gonna have the wrong result. And this bring to the last point, where, for instance, for a simulation you have a torque really high without being able to explain why. So just to put everything in the context, I will run a simulation just to show you how it works, and you will see what I mean. For that, I will. Okay, so just as I said, when you start a simulation, let's say, let's call it uh, uh, okay, MSD, well, MSD underscore 01. Okay, the directory is already selected on my side, so I can just click OK. And let's say we want to run a pendulum, so I can start by fixing the depth to 2 centimeter, the width also to 4 centimeter, and the length. Let's do something simple. Okay, and I can just do this. And I'm working on a 2D side, but actually it's a 3D model, so I can even change it for you to see. So it's a 3D model, but I can decide to just work on the 2D plane. So this is a pendulum, so it will be really easy. I just apply a revolution between the grounds and the path, and I select this point. That is a coincidence between the origin of the grounds and a local coordinate system. Actually, it's a path coordinate system instead of the path. And again, that is it as simulation. I can just directly go and simulate it. That is a mistake because added density properly. I will say, okay, 2 seconds, the time step, let's say 200. Now it should be smooth. Okay. And again, as I said, I can run it again. I can just come back and run it. It doesn't take time, but it because the system is simple. It will be more difficult if it's we have something complex with 1,000 parts and not even 1,000 parts, but you get that easily. So just press on animation and you can have it without running it again. So it can save also the memory inside of your computer. Once you are done with the simulation, and once you are done with the simulation, no, actually there is different aspects on the simulation that, sorry. Sorry. So there is different aspects on the simulation that can be I can talk about, but I will just try to keep it simple for this time, because the point of the lecture the lecture is to give you an introduction for those who will be interested to more training or more information about the system or about the simulation. You can contact me and we can discuss what will be your needs. So when you go to the post processor, as I said, we have the choice between the plot and the animation. So there is more of that, but we're gonna keep it simple. When you go to the animation, you just have to load the animation, and as I said, you can split the space to have two, and I can just go on plotting on that side. So when I'm on that side, to move from one side to another one, you just have to click on it, and you actually see that there is a shift. There is a shift on the view. So just make it wired like that, and I will choose. Let's say I want on the no, on the result. I want to work on the joint and the torque applied in one direction. Let's see like that. So we have the torque applied in one direction that is extremely high because it's 1 million Newton meter. That is about 1,000 Newton millimeter. Sorry. That is extremely high. That is about 1,000 Newton meters. And this is also one of the downfall of using a perfect joint, because it can give some particular results. So that's why it's always important to refine the system as much as possible until you get a system close to the reality, because now you can start asking why we have this result. This is just an insight, but it's better to ask why we have the result afterwards. We have the same case in X in the Y direction, in Z direction is 0 as expected, and we also have the force. We also have the force applied here. So all of those results are meant to be analyzed. It's not something to take. You need to answer to the question why this happened like that. So when we go on the part side, this was everything that I was applied on the joint that is located here, and I can even animate it just for you to see. Okay, I'm trying to move this one. So I can go on this side and animate the system, and you can see on that side which part of the simulation give which result. So this is really important when we have a case to be analyzed, to know exactly what happened when. On that case is really important. It is really easy to understand. The pendulum is going, decelerating, then accelerating again, and this can continue forever because we are using a perfect environment. That means there is no resistance from the hair that is supposed to slow down the pendulum until it gets zero. So this pendulum can work like this forever. And so from there, we can already see that the result is not accurate. If we want to take to account the resistance of the hair, we need to couple Adams with a CFD software. We can provide that force, or we can assume that the force that is applied on it and run a script at the same time as the simulation to create or simulate that force in the same time that the movement is going on. So this is about it for this demonstration. I can carry on uh, I can carry on with the presentation again. So as I said, so now we are going to the world of rapid prototyping. So when we do a rapid prototyping, the most important thing again is the data that can be subtracted from the simulation. As I said, in some case, but this is basic. When you get to write a report, you don't just put pretty picture. You need data and you need explanation on what is going on. So the easiest and the most efficient way to get those data is to do the simulation. This is available for any type of simulation. And in Adams, we need to keep in mind two concepts. Is the first one is at the part at the design level. So when we design what need to be, what you have to keep in mind when you want to design, when you are designing or you are working on Adams. And on the other side, at the force level, is the second concept that you have to keep in mind is which type of force or which type of data I can get from the simulation, how to analyze it, and how to evaluate it, because this is really important to know that your simulation is accurate. Most of the time is required for engineer to be able to run a end calculation of any simulation they are running. This is it's less popular now because industry engineers tend to jump directly to simulation, but it's really important. It's really important. It was even more important 40 or 30 years ago, when engineer from the Nel, for instance, was doing all the NCAC by hands with their reports just next to the simulation results. So it was a way to make sure that the result was an easy way to get the answer for a complex result, but the checking was made anyway. So so on the design level, we have the parts, geometry, material mass, and also moment of inertia. That is really important. I will show you again how those components are assigned in the model. Then we have the concept of degree of freedom and redundant constraints, and which is just a accident of constraint. When you over constrain your system, maybe you can either over constrain your system or you can make two constraints works against each other and against one another, and this we create an error. The system can be under constraint. That means you still degree of freedom, but if you remove twice the same degree of freedom, or let's say you put on the same system two motion that goes in two different directions, you will have a result, because now you are doing a redundant constraint. It's not over constraint, but it's redundant. Then we have the principle of joint motion. That's actually what put the system together and make it move, and also down the measure that can be taken out of that. On the part level, when you create a part, you got this tree that will okay. you got this tree that will actually, it's made of parts, geometry, and reference points. The particular thing is the geometry is not required to run a simulation. The geometry is important if you want to if you want Adams to automatically calculate the mass and the moment of inertia of the system. But it's not required because those values can be changed. You can assign it by yourself, and I will show you that just in a moment. What is really important is the center of mass and the marker inside of the part on its own. And if you don't have any geometry, you can still assign it. Directly. And the thing is, when you create a geometry, or when you import a geometry, Adams will directly define what is the center of mass, will apply two markers. It depends, but most of the time it's two markers. And it will also give him a mass. And by default, it always gives the density, so the property of the steel to any part that are created or imported in Adams. This can be changed. This can be changed afterward, and I'm sure how in the same way. Then we have, I mentioned it earlier, the center of mass. It's created directly when you create the geometry, but then the center of mass is linked to the concept of local coordinate system, and also, oh, the last one is not there anymore. Okay, so it's related to the concept of local coordinate system and global coordinate system. So technically, the global coordinate system in Adams, it's actually a rigid coordinate system attached to the ground, and this defines the zero of the zero of the system. By definition, everything is related relative to the ground. That means to the global coordinate system. Then we have the local coordinate system, and in that we have two types. We have the marker and the path coordinate systems. Technically, the marker is just local coordinate system that can be either are had automatically by Adams on your model, or it's or you can add it manually. So it's added. I can probably say it. No, okay. Let's do it like this. The path coordinate system and the marker is something that is defined by Adams directly in the model when you implement it, when you import it, or when you create it. But if you need for some reason to add another marker or a local coordinate system, you can add that one. By definition, the path coordinate system, that means is every measurement will be made relative to that one, to that point, will be the center of mass by definition. But this is something that can be also changed if you want. And this is just an illustration of what I mentioned. When we have the global coordinate system and the path coordinate system, that is actually the main local coordinate system. And we also have the global coordinate system and the marker. So technically, technically, the marker is always related to the path coordinate system, to the global one, and again, for any reason, if you want to add it, you can add it, and I will show you how. And then we have the joints. As I said, the joints aim to attach two parts and also remove the degree of freedom that those parts has to each other. So we have two type of joint. We have the transactional joint Like for instance, the cylindrical joint or the translational joint is the translational type of joint. And we have also the rotational type of joint. For instance, the spherical joint or the revolute joint are also rotational joints. And to better explain that, I will give you an example of a drive line that we can find. Typically, this type of drive line is it's something that you can find in military vehicle when you have the engine and the transfer case that are in two different places, and you want, but usually it's really complicated how the power must go from the engine to the wheel. And in the type of cans, for instance, a char or a tank, sorry, you you don't usually have everything aligned like in the car. So in that case, you need this type of drive line who actually is made of hook joint and revolute joint. So I will use this example to explain the concept of parts, local and global coordinate system, and also the joint in Adams. I mean. So I will not save this one. Just open a new one. Okay, I will just open this one. Oh, there was also wanted to ask, I'm asking a bit late, did you started recording the session for those who are not there?
Yes, Gal, I'm still recording, so everything is still good on my side.
Ah, okay, okay. I should have asked in the beginning. Okay. So I will just open a new model, call it MSD. So okay. The working directory the same, the gravity, the unit are the same. Okay, I can just open it. I will use a cylinder. It's better to fix it, otherwise it becomes just difficult to manage. Okay. I will just keep it the same. Yes, it looks like. Oh, okay. So I will just apply the revolute joint in between this part. Oh, okay. As you can see on this part, only one marker has been assigned on one side of the cylinder, not on this one. But if I want, I can just come here and add one myself. Choose or add on the parts. So select the parts, select the point, not precise, and then I have a marker on that side. So that's about it on how to add a marker. This is really important. This is really important because even though in that case, this point is virtual, it doesn't exist actually, but if you put a cursor on it, you will find it. So on some geometry is not useful. And if I had to add at this particular point a joint like I want to add now, I add We will join by selecting the ground. Actually, we select the ground just by clicking on the working grid, and then the parts. And then here we have this, but again, we have to move it since it's not applied in the right direction. So I will just modify the joint a bit. Oh, no, I didn't click on the joint. Okay. So I can double click there to modify it. I can select this, rotate about the y-axis of 90 degrees, and just select this. And now the joint is at it's at the right or with the right orientation. Just apply. Okay. Okay. This is exactly the same case for the part underneath here. Just to show you, I will okay. So I will not add a marker here, but you will see that we are able to select a point at this stage. This is just because the shape is simple and Adams is able to pick it up actually what I want to do. But when the shape become complex, it's always better to assign it. So I need to rotate it around the x-axis, this one, to have it align with the with the cylinder. Otherwise, I won't be able to spin it. So again, I can just select the orientation like this, 90 degrees around the x-axis, and that's it. Okay. Then I will add the hook joint between those two. So since I'm working on a plane, I don't have to worry about the alignment of the cylinder because I know that they are aligned. So the hook joint will work. But if it was too offset, it could have been a problem. Even if Adams always try to solve those type of problem, but it's always better to have an accurate system on that one. So I will just create a hook joint, this one, between those two parts at, let me zoom a bit, at this point, following this feature and this one. So usually the good thing to do is to always do a sanity check to make sure that everything is fine when you are modeling a system. The reason is if you put too much constraint without checking, you can reach a point where you just how can I say it? You put too much effort and you didn't realize that you made a mistake, and now it's difficult to find the mistake. Since you didn't check at each step. So it's always important to check, to do sanity check with your system, especially when you start. Then we have I will apply the hook joints on this face, between those two. So it's between those two at this point, following this feature, and following. Okay. You see, now the problem is not pointing at the right direction. And the reason is very simple, is because it is not, I didn't define any, how you call it, any mark pointing to the right direction, but I can still make it. No. Okay, for a real reason it's not working, so I will go the way around. Since I have this marker, I can design between this one, and this one. Oh, Mm. No. It's better to use it that way. Oh, you see, this is the reality of anyone who deals with design. Even if you are used to something, you can have you can always have an issue at a certain point. Okay, this is because there is the difference between both of them is too large. I cannot. Yeah, the difference between both of them is too large. I have to change it. I have to change it a bit. And this is what I meant by the offset. Now I cannot pointing properly because there is an offset. And if I leave it like this won't be able to spin. And if I run it right now, you will find the mistake. So to solve this problem, I have to do it to align it to make sure that the joint will work. And this is okay. I actually created this part, but on the real design, you will always pick up that it's not aligned enough to apply a hook joint. Uh, I will just delete that one. Okay, I can change. Oh, no, this is the extension. Mhm. Okay, it's going on your right. Technically, it should be fine now. Okay, look like I still have the same issue. Let's see. Okay, this is the reality of if doing a live demo. Okay, I don't know why I'm struggling with this one. Not supposed to be like this. I'm not sure that this one will work.
Sorry, Gal, just a quick question from my side. Although we're now working with a fairly simple geometry, would it not be easier in this case to, in any case, specify a marker on this left-hand side of the cylinder to get that
Yes.
vector that you're trying to construct.
Yes, I'm trying. I will do that. I was trying to avoid that option, but I think I don't have a choice. I have to. Actually, I try to avoid because now I have to find the right angle to turn this one. So this is also the reason why I was trying to avoid it, because I'm dealing with complex geometry. The good thing to do with this in that kind of situation is to technically apply it on this one. Okay, that's correct. I'm a bit worried about this offset, but try it. Let's try it to see if it's working. If it's not, we have to make it seem easier. Oh, yes. Okay. For this one, I have to apply either a torque or a motion. So I will rather apply a torque on this one to make it work. Fix to a body. No, there's a mistake on this one. Okay, if I apply a torque of 100 constants, normal to degrees. Okay, that is correct. So I can just run the simulation and see. So you see, because of this that is not aligned, I cannot run it. So what I will do is I will just the thing is I kind of see this thing coming. So what I will do rather is to use the model that I prepared. So this model doesn't have a problem because of how close it is. The problem is it's sometimes difficult to find exactly how close it is here. So on a model like this, we can actually run it and you will see that it will work. It's just a pity that I couldn't create it from scratch right now, but it's better to have a plan B instead of just spending a lot of time on one model. Sometimes it's happened that for a simple thing, you can spend a lot of time because you don't have the right coordinates, but it's something that can be solved. Just that it can take time sometimes. So since I was talking about the part, when you create a part like this and you go on modify, you will see that it's already assigned that those properties are already assigned. So the Poisson ratio, the Young modulus, and the density. You can either compute and find the mass and the moment of inertia based on that, or you can have like what we call user input. So literally I can change and say that I want my mass, I want my model to be 50 kilogram or something like that, apply it, and it will be applied and it will work at ease. On the side of the joint, on the side of the joint, as I showed you, we have the joint between those two, and those two, and also between the cylinder and the ground. The revolution remove actually 5 degrees of freedom and leave only one rotation around one axis. The hook joint actually doesn't remove any rotation because it allowed the part to rotate around every axis, but does remove any translation. And it's like this. There is actually a list of joints that you can find here on connector, and each of them remove a particular type of degree of freedom. For the part, as I said, even if for, let's say, for part 4, this one, you decided to delete the geometry, you can still have a part here that is identified. So it's when I select it, it's still gluing up, and technically I should be able to run it. The thing is, we don't see just the geometry, and everything that is linked to the mass, and everything must be now written down on the characteristic. But technically here I won't be able to compute it anymore since I don't have any geometry anymore. So it's that way that Adams work. So just to carry on the presentation, then after talking about the part, global and local coordinate system and a joint, we have now we don't have to measure the data inside of the system, and this happens by using global and local coordinate system. Basically, when you run a simulation, everything comes from the measurement between the global and local coordinate system. That means the part coordinate system will be the measurement will be taken between the part coordinate system and the global coordinate system. And most of the time, the standard measurements or the standard measure are the torque, the force, the displacement, velocity, and acceleration. This is basic in terms of measurement. But if you want something else, or let's say you want the displacement between 2 points inside of the system, or you want to know what is the orientation between 2 different coordinate systems, or how it evolves during the simulation, that's when you need to specify them, and there is a way to do that. So as I said, these are the typical type of simulation that can be done inside of the system. We have the center of mass position, velocity acceleration, angular velocity, angular acceleration. This is just a list, but there is a bit long. It's a bit longer. When you want, as I mentioned, when you want to do specific measurement, or you want to take specific measure, you need to use this part where you can either use the standard measurement, or you can define them manually by yourself. And by doing that, we have this example when you have the general measure that can be taken here. There is actually a different way to do that. The point-to-point measure is what I said when you have 2 different points and you want to see the velocity in between them of one according to another one, or you want the orientation. That's just the one I mentioned earlier, where you want to define the evolution of angles between 2 different axes, or 2 different markers. Then we are on the second level. On the second level, I mentioned the first level when we had to think about the parts, and on the second level when you have to think about the force that is applied during the system, and all of those the force are the spring damper, the torque, the contact, pushing, friction, and there is others that you can find. And to illustrate this, what I said, I will show you an example when you have a simple model. It's a slider crank, but now the slider crank where we have contact between parts and we also have a spring damper. So if I ask you to find uh, the speeds, the speed or the torque needed to get the slider to move back and forth at a certain speed or to stop at a certain point, you can find it easy. You can find it easy, quite easier with a because with with a slider crank, it's kind of easy to find it. Okay, it takes a little bit of time, but it's still easy to find it. But now when you start adding parts like like spring upper, when you start adding bushings, when you start adding other components, it becomes difficult to find a solution. And at the end of the day, 30 minutes of calculation won't match 2 minutes of simulation. So it's kind of trade-off you have to take when you are working in industry. But it's really important to always do a sanity check of what you are doing by doing a NCALC to have an idea of where you are going. And to just illustrate the concept of contacts, I will take something that is way easier than this example. Let's take no. Okay. Oh, I didn't change the name. But for something like this, I can keep it that way. Yeah, can keep it that way. Change this one. No, this one is a mistake. Okay, this one is more accurate. I will just make it 40. Like this. And I will create connector between them. So it's the ground and these parts between these two parts. And between these two parts, I will also create a contact force. I'm using basic parameter between them and apply it. Okay, well, apply it twice. And just run the simulation like this. So again, 2 millimeters, 200. Ah, yes. This is why it's really important to always do a sanity check, because I forgot the translational joint between the ground and the piston. That direction. Okay, the simulation is too short. So let's push it to 4 seconds, 400 steps. So as you can see, there is a contact force with that one that will not exist if I can just remove that. So I can deactivate it. I'm not deleting that, I'm just ignoring it during the simulation. And when we do that, there is no more contact forces. And I can actually plot both of the system to see what is the difference between them. Okay, I didn't save the last simulation. I should have done that. So now I can this is a pity. I should have saved it. But again, when you want to make it more difficult and add, for instance, a spring damper. Let's say you write a spring damper here with a stiffness of 101% of the stiffness between this and the ground. I didn't add any preload, but now the behavior of the system change. It's not even moving. I actually have to add a force to make it move, otherwise. Okay. Otherwise, it's not just moving. So these are the concepts. These are all the concepts that you have to take to account. Is when you want to ask you want to ask a question, you want to answer to a question, how are you gonna answer? How are you gonna answer it? And I think for this one is self-explanatory. I've done a couple of simulations so far, and this will be the last slide of today, at least on my side, because so far I've been presenting simple simulation, but there is complex system that can be simulated, and I can actually just show you that this is at an advanced level. It's just to show you, it's not to learn now, because you need a lot of practice on the first version of Adam that I show you to do something like this. But I can run either something like this or something even simple by using a spring damper. I can use a spring damper model. A suspension, I say a spring damper, sorry for that. A suspension, I can open an assembly. Why is it not selecting? So again, this one is when you are really advanced and you want to test a suspension system, or for different configuration. You can now see the complexity, and this type of system is difficult to do it by hand. So to do a simple simulation, I will test a parallel wheel travel for a output. Let's call it tests 0.3, because I run it twice already. All the parameters is straight. I can apply. Okay, that's it exists already. Let's say it 4. That already exists. Okay, I don't know how many of them I run today. Okay, I didn't run the full car simulation because it can sometimes take time, but with this one it's just a couple of seconds, so I can just review it. Animation control. And actually, this is just the reaction of the suspension to a certain displacement of the test rig. So those two are the part of the test rig, and the wheel also is attached to a suspension system that the one we are working on. And this is a simple test that's usually run in car company. And if you want the results, you can go on review no, system animation, sorry, review, post-processing, and we have different results for the displacements. Okay, maybe this one. We have displacement of this left string around x, y, z. It's because the simulation is short and the result is not that long, but it's about it. We can go really hectic in terms of simulation, but this is it's just a simple example. And that will be about it for today to my side. I don't know if there is any of you who has any question.
Yes, thank you very much, Gail. For anyone that has questions, you're more than welcome to post it under chat messages or raise your hand, and we'll get to your question. Perhaps less of a question and more of a comment from my side. I think it was in one of the first slides that you showed that you basically follow a design process where you first build, then you test, and then you start to improve through some sort of an optimization technique. And it's quite interesting that you mentioned this as well. I think it's something that we usually overlook whenever we start setting up new designs is the validation part. And you also mentioned that if we give the improper inputs to the system, we're going to get the wrong output as well. I believe in the IT environment, they call this GIGA, or garbage in, garbage out. At the end of the day, the nice thing about something like Adams or using DAP-BC and doing some sort of a validation is that you then ensure that you don't give, well, in this case now, garbage input to the system to solve. So it makes it much easier once you jump into optimization to make sure that the results that you get at the end of the day are reliable, since you did test some sort of an initial design. And this was also something that we sort of covered in the first assignment for the students as well, where you have some mechanism that you set up, you do validation, and you can physically compare whatever hand calculations or classical methods results you got to the actual results that you got from DAP-BC. So I think that's just one of the comments from my side, and something that's interesting and one of the primary points as well from your presentation today. Yeah, yes.
But you're perfectly right. As I said, the simulation is as good as the engineer. It's a tool. It's not a magic way of getting answer out of your problem or out of your question. We must understand what is going on. We must understand how the tool works. We must understand how the theory works. Otherwise, we are just pressing on button and expecting for the best. So.
Definitely, and I think that's something that we see across from DAP-BC onto Adams as well. At the end of the day, it's not about the actual software package, it's your application of the design principles and your ability to solve the problem from an engineering judgment perspective that really governs what results you're going to get out and how effective your results are going to be. So yeah, I completely agree with that as well.
Exactly. I don't know. I don't see any question. So I think it was clear for everyone.
Yes, I think everything, yeah, I don't see any questions on my side as well. So in that case, thank you very much, Gail. If anyone still has questions, you're more than welcome to email me and I can forward that to Gail and we can answer your questions. But I think that is then everything for our first guest lecture. So thank you very much, Gail, and I'm looking forward to seeing you in our next lecture.
Thank you, Devos. See you.
Thank you.